In the previous video, we looked at the first type of fragmentation, which were alpha cleavages. In this last video, we're going to look at the second type of fragmentation, which are rearrangements. Now, a rearrangement is defined here as it's a fragmentation that involves intramolecular abstraction of hydrogens. So in the first video, we saw what a hydrogen abstraction reaction is, which is that it's an exchange of a hydrogen atom between two species, radical species. So that's the type of process that's going to be involved in this kind of rearrangement here. If we go a bit further and we try to compare the two types of fragmentations, well, what we already saw about alpha cleavages in the previous video is that an alpha cleavage can be recognized on a mass spectrum because if we start with a molecular ion of even mass, it would lead to the formation of odd mass fragments. Well, a rearrangement fragmentation can be identified by the fact that if you start with an even mass molecular ion, you're going to get an even mass fragment. So these are two very, very important aspects that you want to keep in mind when you're trying to explain the origin of different fragments. Look at what type of even odd or even combinations you have. Now, the first type of rearrangement fragmentation involves the loss of water from alcohols. It's a very, very common fragmentation, very, very common rearrangement. What you want to know is that first, you're not responsible for the mechanism that is at the bottom of this slide. We're going to look at it, but you do not have to remember it. What you really want to know, though, is that losing water, mass of 18, is very, very common for alcohols. We're losing water as a mass of 18. That's an even mass. That's why when we have a loss of an even neutral molecule, we go from even to even. You're not responsible for the mechanism for this reaction, but let's look at an example so that you understand why it is called a rearrangement. So if we look at the mass spectrum that's provided here, we can see that the molecule of interest is 1-pentanol, which has a mass of 18. On the mass spectrum itself, we actually don't see the molecular ion. What we see is the M-1 peak at 87, so it lost the H of the OH group. But what we do clearly see is the fragment at 70, which corresponds to 88 minus 18, which is the loss of water. Now, how did that fragmentation rearrangement proceed? Well, as you would expect, when you ionize this molecule, you're going to first remove one of the electrons from the electron pairs on oxygen to form a radical cation. And then once we have a radical cation, the loss of water usually proceeds by an intramolecular H abstraction reaction, where the radical that we've formed earlier, it goes up and abstracts a hydrogen somewhere else in the molecule. I've shown it at this position here just for illustrative purposes, but this hydrogen could be removed at other places in the molecule. The main aspect, the main thing that you want to understand is that when we remove that that hydrogen in an intramolecular fashion, we're still left with something that has a positive charge. We have now not only something that has a positive charge and a radical, but as you know from Chem 250, this is just a protonated water. This is what we use in Chem 250 to transform an alcohol into a great leaving group. So this water molecule here that's attached to the alkyl chain is a very good leaving group like we saw last semester. So once you've conducted this intramolecular H abstraction, what you form is something that has a great leaving group. So it just leaves by itself. we form water on the side of the product and the carbocation, which is the species that's detected on the mass spectrum. So again, you're not responsible for this mechanism, but I want you to understand that this is a very different type of rearrangement from the one we saw previously, because this one proceeds by H atom abstraction reaction. Not only that, but it also leads to the loss of a neutral molecule, so that we see even mass molecular ions going to even mass fragments. Now, the second type of rearrangement is one that is going to look weird, and it kind of looks weird when you look at the mechanism, but it's so common that we need to look at it. And in this case, the mechanism, which is quite a bit complex at first, is actually exam material. And one of the reasons why it's exam material is that not only is it a great mechanism to ask in exams and problem sets, but also it's a very popular type of rearrangement that's asked in, for example, our final ACS exam. So we really need to look into it. So this second type of fragmentation through rearrangement is called the McLafferty rearrangement. The McLafferty rearrangement applies under these conditions here. So it applies to aldehydes and ketones, but not only aldehydes and ketones, they have to have an alkyl group that's attached to the carbon group that's at least three carbons long, so that we can have the mechanism that's is going to be shown here operative. Now, you'll see that it looks a bit weird because at first, because you've never seen this rearrangement, and because you've never seen this mechanism. But it is very, very common. And if we go back to the previous example that we had, where we looked at alpha cleavages in this ketone at the bottom of the slide here, earlier we had identified going from 100 to 15 as an alpha cleavage, going to 100 to 43 as an alpha cleavage, and odd to even, and even to odd combination. Well, if you go from 100 and we try to explain the fragment at 58, we know that this is going to involve a rearrangement, because it goes from even to even. And this one actually is indeed the McLafferty rearrangement product. The McLafferty rearrangement for this species is what's shown at the top here. If we start with the ketone that has a mass of 100, we ionize it to form the radical cation, and then through a cyclic mechanism where the hydrogen, a hydrogen that's on the chain of 3 carbons, 1 carbon, 2 carbons, 3 carbons, the hydrogen that's on the 3rd carbon gets abstracted in an intramolecular fashion, so it ends up on the oxygen on the side of the product. And then what we expel through a mechanism that involves a cyclic movement of electron is a neutral molecule. This neutral molecule has an even mass, so that if we start with an even mass of molecular ion, we're going to lose an even mass, so that the corresponding positively charged species that's going to be detected on the spectrum will also be an even mass. You need to learn this mechanism. You need to learn to push these arrows correctly. In order to do that, I would encourage you to draw this mechanism several times so that you can practice it and you just verify your answer with what is on this slide here. So here's just an expanded version of the scheme that was on the previous slide, so that we can look at the mechanism more clearly. In order to draw this mechanism, you could start anywhere on the radical cation, but I think it just makes sense to start on the lone electron that was created during the ionization. And we know that we need to form this OH bond in the product here, so that we need to involve a hydrogen abstraction reaction involving the oxygen and this hydrogen. So that the first step in our mechanism the first step in drawing our mechanism could be that we are going to draw this hydrogen abstraction here. So we start with the lone electron on the oxygen, we put it where it's going to end up, so where the OH bond is going to end up. And then we need to break the bond that binds the hydrogen to the carbon that it's attached to, so that we take one electron of this bond and we put it where the OH bond is going to be. So now we form the OH bond. What we've seen before when we do hydrogen abstraction reactions is that the second electron from a bond that we're trying to break, so right now we're trying to break the CH bond, would go in the opposite direction, and would in this case it would go on the carbon. But then if you look at the product that we need to form, there is a CC double bond, so that the carbon on which we would throw the second electron of the CH bond that we're trying to break is actually involved in the new CC double bond. So in our mechanism, instead of drawing an arrow that takes the second electron from the CH bond, put that electron on the carbon, and then take that same electron and form the CC double bond with it, what we can do is just take the electron straight from the CH bond and put it where it's going to end up, which is the CC double bond that's forming in this reaction. So then up to now we've partially formed the CC double bond, the alkene that we need in the product. The way that we're going to complete this this new pi bond is to take one electron in this CC single bond here, and we'll put it here. So now we've created the pi bond in the product right here. As we're doing this, we've started to break this carbon-carbon bond here. That's the bond that attaches the two different products together. So now that we've started to break this bond, let's just finish it up so that we can isolate the two products. The way that we're going to break this carbon-carbon bond, again, we're just breaking a sigma bond through a homolytic reaction. So as we've done before, we could just take the second electron of this CC bond that we're trying to break and put it on the carbon. But as you can see, again, this carbon here is involved in a CC double bond in the product. So instead of taking the second electron of the CC bond that we're trying to break, put it on this carbon, and then take that same electron and put it, move it to form the alkene, we can just take the second electron of this CC bond and put it where it's ultimately going to end up, which is where the CC double bond is going to be. So now we've broken the bond that binds the two parts together. We've partially formed the CC double bond in the product. The way that we're going to complete this CC double bond is we're going to take one electron of the CO double bond and we're going to put it towards the CC double bond. As we're doing this, you can see that in the product here, the CO double bond that was in the starting material is now a CO single bond in the product. Right now, we've taken one electron of the CO double bond, the pi bond. So there's one left. So that electron that's left from the CO double bond, we're just going to put it right onto the oxygen. And that completes our mechanism here. All right, so let's review what's going on here. Let's just redraw it, and then we'll look at what happens with the different atoms here. So let's erase all of this. So we start with the lone electron. We put it where the OH bond is going to be. We complete the OH bond. We start forming the pi system of the alkene. We finish this pi bond. We're going to form a new pi bond on this side, and as we're doing this, we're breaking this bond right here. We're going to finish up this new alkene here, and then we're going to take the electron left over in the CO pi bond and put it on the oxygen here. So if you follow all of these arrows, you can see that you're going to form this neutral alkene here. You're going to form this species. This species is a radical cation. It's a cation, so that's the part that is going to be detected on the spectrum. So this species is what we're going to detect, whereas this one is just a fragment that is lost in this reaction. Now, perhaps what's most uh, uh, difficult to figure out at first is what's going on with the oxygen in this reaction. It's actually quite straightforward when you look at the overall transformation. The oxygen starts with a lone pair, it starts with a positive charge, and it starts with a lone electron. The positive charge is not involved at all when you drew the mechanism earlier, so it's still present at the very end. The lone pair is also not involved at all, so it's still present at the very end of the reaction. And then when you start your mechanism, you do take this electron away, so you remove it and you involve it in the sigma OH bond. But then at the end of the reaction, you take an electron and you put it back on the oxygen, so that overall, you haven't really changed the electronic environment. That if there was a lone electron to begin with on the oxygen, it's still present at the very end. All right, so make sure that you practice this mechanism a few times. I would just say, just redraw it and then verify your answer with what's on the slides here. And to give you an opportunity to practice this mechanism, you can try to work on the problem that's on the next slide, the last slide here.